Okay, so welcome to this video lecture. So we are going to have examples on a simple strain. So for the first problem, we have 20mm diameter rod was subjected to tension steel test where 600mm length was placed. The following data were recorded relating to force versus its corresponding deformation. So this is load in kilonewton, deformation in millimeters. So with the loading of 57.2, it has an elongation of 0.2145 in millimeters, and we have 171.6. There is a corresponding 0.4895 millimeters elongation. So we are tasked to compute the strain due to the first loading and the strain due to the increased loading of 171.6 kilonewton load and the Young's modulus of elasticity. The problem is simple. We'll just have to apply the principles of a proportional limit. As a solution, of course, in order to obtain the sigma, we need to know the area. Okay, and from the problem we can see here we have a 20mm diameter rod. So simple formula to determine the area, we will yield to 314.16 square millimeter, and then from that we will determine the sigma for the 57.2 or the first loading. Okay, so this is being multiplied by 1000 to make it in Newton, and then divided by the area, we will yield at 182.07 megapascal. So for each corresponding strain, so this value has nothing to do with the strain because strain is an independent formula. Strain is equal to the deformation all over the length. The length is 600 here, and the second or the first deformation is equal to 0.2145. So by quotient, we have this 3.575 times 10 raised to negative 4 millimeter per millimeter. And then we will do the same with the second loading. We have 171.6 times 1000 divided by the same area. We will yield at 546.22 megapascal. So for each corresponding strain, so it is observed that here we have an increased deformation to 0.4895. We'll just use that and then divide it by the same length. We will have a bigger strain equivalent to 8.158 times 10 raised to negative 4 millimeter per millimeter. And then from this, we can now graph the stress and strain diagram. We can observe a straight line there, and between these 2 points, the difference between delta is actually the gradient on the y-axis, and the difference between the horizontal axis is the gradient on the x-axis, which is the delta deformation or the delta strain. So for the Young's modulus of elasticity, we get the slope of the line. We will just have to subtract the difference on the y-axis, which is the sigma, or 546.22 minus 182.07. That would equate to 364.15 megapascal. And then delta strain is equal to the second strain minus the first strain. So we will come up with 4.583 times 10 raised to negative 4 millimeter per millimeter. And then applying the modulus of elasticity, sigma or stress over strain, we will use the change or the delta on the y-axis and the x-axis. By dividing that, we will yield to 794,566.88 megapascal. And that will be our answer for the first problem. Problem number 2. Recording in a stress strain test yielded 41.33 megapascal. So this is the stress. So it has a corresponding elongation of 106.67 times 10 raised to negative 6 millimeter per millimeter. So by the unit itself, this is a unit less, so therefore it refers to the strain of this particular unit load or stress. Same true with the second unit load, the 100 megapascal unit load. It has corresponded to 258.09 times 10 raised to negative 6 millimeter elongation. So meaning this is in terms of unit deformation. So first, we're gonna compute modulus of elasticity, and then second, we work for the strain for a corresponding stress of 60 megapascal, and then we compute for the original member length for an elongation of 0.4 millimeter and a stress of 60 megapascal. By the way, let us have this unit millimeter per millimeter. So this should be millimeter per millimeter. So therefore, from that, the same procedure to compute for the modulus of elasticity, we'll just have to get the differences between the sigma values on the y-axis and the echelon values on the x-axis, the stress and the strain. And then from this, the delta stress and delta strain, we can derive our modulus of elasticity. And it yielded to 387,465.33 megapascal. So the graph portrays a straight line, and therefore these values are within the elastic limit or within the proportional limit. So that is the first unknown. And for letter B, what would be the strain at 60 megapascal stress? So we will employ the same formula what we did in the first unknown. We just simply get the difference between the 2 points. So this time we will be considering another point wherein the stress is 60 megapascals. So this is 100, this is 40, therefore 60 is in between those points. So what we do is to use the upper limit, okay, instead of the lower limit to derive our modulus of elasticity. To derive the strain, I should say, the strain. Because actually, if we could graph it properly or appropriately, we can just project this down and then get the strain. Because the second unknown is the stress for this particular, or the strain for this particular stress. So we'll just have to use the equation for accuracy. So here, as we can see, E was already derived, and E is actually the slope of the straight line here. So we have the same slope, or a constant slope. It is not changing. Therefore, we will adopt the same slope to compute for the strain of the 60 megapascal stress. So here, I'll just use the upper limit 100 instead of the 40 41.33. So I'll just use 100 megapascal, or the upper limit, to solve for the strain of 60 stress. So we'll just have to apply this formula and then deduct or get the difference of our delta sigma to get the change in strain. So we have 1.03 times 10 raised to negative 4 millimeter per millimeter. So next, we then solve for the E1, or echelon 1, or the strain 1. Strain 1 actually refers to your 60 megapascal. By the way, this is not yet the answer. This is the change, or the change in strain considering the upper limit. So therefore, this is further expanded to its formula, wherein the upper limit strain minus the lower limit strain, and we are actually getting the lower limit strain, which is 60. So the strain for 100 is actually recorded to be 258.09. So let us check that one. Okay, that's it. 258.09 for 100 megapascal. And then from that, the strain for 60 megapascal stress is computed to be equal to 1.549 times 10 raised to negative 4 millimeter per millimeter. So in short, 1.03 times 10 raised to negative 4 minus, or this is just transposed to the other side, we will yield to this answer. And then for the member length of this corresponding strain with deformation of 0.4, what is the length? Okay, so from this strain at 60, or the 60, see the sigma here has 60 megapascal, and we have computed the strain to be equal to 1.549 times 10 raised to negative 4. This is a unitless. Okay, if we have to consider a delta of 0.4, what would be its original length? So these are the three conditions for us to derive L. So we'll just have to apply the formula for strain, that is delta all over the original length. This is given under the conditions on the problem. We are looking at L, so we'll just have to use this one, strain. Okay, so substituting, cross multiplication, and manipulation, can now derive the original length, which is 2582.31 millimeters. Okay, so next, so for problem number 3, the following were the recorded data obtained from stress strain of a steel bar. So starting from 0, so we have here an increasing load, or actually this is an increasing stress in megapascal. Of course, the strain would also increase. So we're going to compute here the modulus of elasticity, modulus of resilience, and modulus of toughness. So let us start by graphing the data given. Okay, so this is a direct graph because your given is already in stressed. Okay, this is already in terms of stress, and this is already in terms of stress. It is just a matter of putting those values into your graph. Here's the graph. So what is the purpose of graphing it? Because we cannot trace the fracture point, because the fracture point is actually the point of transition between the straight line and the curved line, and the fracture point is found to be on the first point or the value, because the second value would not bisect this line up to the point of origin, meaning therefore this is the fracture point. So we can conclude here that it is obvious that in the graph that the fracture point or the end of the proportional limit is at the first point where the stress is equal to 152.67 megapascal. So within the proportional limit, we have the modulus of elasticity by Hooke's law, and Hooke's law is modulus of elasticity is equal to stress all over strain. So we'll just have to apply that one. So the stress is 152.67 all over each corresponding strain, 0.000533. Will arrive at a modulus of elasticity equivalent to 286,435.27 megapascals. So our next unknown is the modulus of resilience. So as defined a while ago, or on the previous video lecture, so it is just equal to the area bounded by the straight line or the within the proportional limit. So obviously we'll just have to use the formula for the triangle, that is 1/2 base times height. Actually this is 152.67, and the corresponding strain is 0.000533. So we note that the resulting unit here is megajoule per cubic meter. Why megajoule per cubic meter? Because 1 joule is 1 Newton meter. Observe that we are actually multiplying here the stress and the strain. The stress is mega Newton per square meter, or this is megapascals. So we multiply that by meter per meter, and Newton meter is actually joule, so we can combine that by megajoule all over. So we just have to combine this, will become cubic meter. So therefore the resulting unit is megajoule per cubic meter. Okay, that's it. So as simple as that. So next unknown is the modulus of toughness, and the modulus of toughness is actually the area bounded by the whole curve from the point of origin up to your modulus of toughness. So in here, it's already shaded in the graph. We have 5 areas, okay, although these are curved areas, we'll just have to consider here or assume a trapezoidal area. So therefore, this procedure is an approximate of modulus of toughness, because in reality this is a curved line. Okay, so area 1 is the triangle. Okay, so we just have to get here the first value, 0.0407. It was computed for the modulus of resilience, the triangle here. And the area 2, just consider the point here. We have 0.008, the upper limit, and 0.0053. And for the height, this is the difference between the 2 points, the first point and the second point. So we do for the area 3, we do the same. We just have to get the difference of the x and y axis. Okay, for 4 and 5 also. So we sum up that, then we get the modulus of toughness equivalent to 0.273. Okay, so moving on to the next problem. So yielding was observed in a stress strain test when the load is 20 kilonewton, and it was applied to a 1.2 meter long structural member. Calculate the allowed axial force to the structural member to satisfy a factor of safety of 2 with a corresponding elongation of 0.6 millimeter. Assume stress at yield to be equal to 400 megapascal and E is equal to 200,000 megapascal. So let us have a review on the factor of safety. Factors of safety is just equal to the yield stress all over the allowable. Okay, remember that what we are using in the design is the allowable. Why allowable? Because instead of using this as a limit, it is better conservative to use this as our design criteria, because we have a factor of safety wherein we cannot allow that the allowable stress should exceed the yield point. So meaning it is a conservative design, but before we're gonna reach this one, we are designing actually the structural member on this sigma allowable, and then from sigma allowable we will derive the corresponding area. Okay, what is the required area from this allowable? Because we are not calculating the desired area out of this, so we are calculating it by sigma allowable. That is considering that we have a factor of safety, so meaning before failure occurs we are designing it, so therefore under this sigma allowable, so therefore our area here should be conservative before failure. So that is the sequence of our solution, and after which, if we could derive area here, and then from the elongation of 0.6, what can we get from here? Actually, if we have an elongation, then we refer to this formula of strain. Strain is equal to deformation all over the original length. Okay, so if we derive this one, then we could refer to Hooke's law. Why Hooke's law? Because within this limit, the material has the capability to go back to its original shape when the loading is released. Okay, therefore, what uh, what what stress can we derive from here? It is actually the prevailing stress, and the prevailing stress is actually smaller than the allowable one. Hence, we have an area that is conservative from this prevailing stress. Okay, so the step here is first we need to design the member by sigma allowable. Step 2, what can we get from the sigma allowable? The corresponding area or the required area. And then step 3 is to work with the prevailing stress, considering the conditions in the problem. Okay, so that is the sequence of our solution. So don't get confused, because from the given in the problem, we start with the stress at yield equivalent to 400 megapascal. So I'm going now to present my solution. So let me erase this one. So moving on to the next slide. Okay, so we derive the allowable, okay, because the allowable is our basis. It is not the yield stress. Okay, so by simply applying the factor of safety formula by cross multiplication, we can derive the allowable stress. So under this condition, we apply simple stress formula. Sigma allowable is equal to P all over A, and then we determine the minimum area to prevent yielding. So 200 is equal to P over A. And of course, we're gonna apply now the 20 kilonewton loading that is actually given in the on the problem. So yielding was observed when the load is 20 kilonewton. So we substitute and derive the area that would equate to 100 millimeter squared. Then applying linear elastic deformation. So strain is equal to delta all over L, and 1200 is actually the length of your structural member. Okay, so from that we can determine your strain. Okay? So what is the purpose in determining the strain? In order to apply the Hooke's law. So again, we apply the Hooke's law because the Hooke's law states that the material will have the tendency to go back to its original position when the load is applied, meaning there is no permanent set yet. So that is how it is done in design. So we then compute the prevailing stress when the elongation is 0.6 millimeter. Okay, so 0.6 was used already in your strain here, and the strain will be used in your Hooke's law, so that this will now be our prevailing stress. Okay, 100 megapascals. And then from your prevailing stress, what is the allowed loading? So we now use the simple stress formula and then substitute all the given. We have obtained already the area. So 100 by 100, or simply your P is 10,000 Newton or 10 kilonewton. Meaning 10 kilonewton here is smaller than the applied load when the yielding occurs. Okay, when the yielding occurs 20. Okay, so meaning having a factors of safety of 2, we have 10 kilonewton as a conservative loading. So in our solution, it is an incident or coincidence that your loading is just doubled. Okay, so as we can see, 20 kilonewton just divided by 2. Okay, then we can arrive with a half of 20 kilonewton. So this is just a coincidence because of the numbers applied here. Okay, so for the fifth problem, so we determine the required diameter and its elongation of the diameter bar CD. So this is actually bar CD to satisfy a factor of safety of 3 when its stresses at yield point is 276 megapascal. Then we're gonna assume a Young's modulus of elasticity equivalent to 200 megapascal. So as a solution, so just the same, we are going to derive our allowable sigma out of the factor of safety. Here it is. So we substitute the 3 given and then the yield stress 276, and then we can get the sigma allowable, and from this we can get the area. Okay, however we do not know yet the value of the force along CD, so we can solve the force along CD by its free body diagram. Okay, so we can see here that we have here a pin connection, so there will be 2 reactions from that, and we assume a tensile reaction here for PCD inclined at 52 degrees, and then 1.5 we'll just have to multiply that to make it in multiply that by 9.81 to make it in a force, or 14,715 Newton weight, because 1.5 here is in kilograms. Okay, so from this you can now take moments at A to solve for your PCD. So we have taken moments at A, so negative PCD, or the vertical component here is opposite your angle, so sine 52 multiplied by moment arm, so we have here 2. Okay, so that's 2, and then plus your weight will have a clockwise rotation by that times moment arm 4 from A, then we equate it to 0, we can get the value of PCD. And then we go back to equation 1, we can now derive the area. The area will be equal to 405.95. So when we divide this one, so from that we can get the diameter, so just equate it to the area of the circular section, circular cross section, and then solve for your required diameter. So we have diameter equivalent to 22.73 millimeters. So to determine the strain with this corresponding diameter, area, and force, we apply the Hooke's law to solve for strain. Okay, so 200,000, actually this is the stress, 92, or the allowable. We have the strain to be equal to 4.6 times 10 raised to negative 4. So finally, to solve for the length of the bar, we'll just have to employ the formula of strain. Strain is equal to delta all over the L. So we apply it to the length of the bar. So the length of the bar is, let us have a subscript CD for the CD. And the length of CD is actually a diagonal of this right triangle. And we can determine that since we have here 2, okay, by function of what? Cosine 52 degrees, adjacent is 2, and the length is LCD. So therefore, the length of CD is equal to 2 all over cosine 52 degrees. Okay, you can see it on the solution. So 2 all over cosine 52, that will be equal to 3.25 meters or 3,250 meters. Finally, the deformation is just equal to 1.495 millimeters. So this is the answer for the 5th problem. So that's it for the first 5 problems on the simple strain examples. So please stand by for your activity and the upcoming video lecture. So thank you for listening. See you on the next video.